and welcome to another TA Instruments Quickstart e-training class. This class is on the Q400 TMA, and my name is Louis Wagesback, and I'll be the instructor for this class. First off, I want to welcome you to this class, and I want to thank you for being a customer. The fact that you're taking this class means that you or someone at your company has purchased equipment from us, and we appreciate that. We've designed these courses to help you, our customers, get the most out of your equipment. So we've designed this course as a real basic getting started course. We'll show screenshots of the software, and we'll show you calibration. We'll talk a little bit about the data. So this is what we're going to do in this class. Now, ideally, we would like that the TMA is sitting on your bench, already installed. If you haven't had the TMA installed yet, that's okay. But what we'd really like for you to be able to do is, as soon as you finish this class, be able to go right there on your TMA and be able to run data. Okay? Now, on this web-based format, you will have across somewhere in the screen, you'll have a little, looks like the buttons on your VCR. You can play and fast forward and stop. And you can do that to go through and play this course. You can fast forward it. You can rewind it. You can pause it. And then you can play it again. Okay? So now what let's do is go ahead and get in this course. This is what we're going to look at. We're going to have an introduction. We're going to talk about how to run a typical sample. And then we'll talk about other topics like calibration, some of the Q400 EM, etc. Actually, I've already talked about this, but the course is designed for new users of the Q400. If you've used the instrument for a while, it doesn't mean that you can't take this course. It just means that the course is pretty basic, so it may not gain you as much as if you're a new user. Okay? Now, after completing this course, what we want you to have out of this is a basic understanding of the Q400, the ability to set up and run a typical experiment using the wizard, and an understanding of other issues such as calibration, sample preparation, etc. Now, TMA is thermomechanical analysis, or the instrument is the thermomechanical analyzer. Now, this measures changes in the dimensions of a sample as a function of time, temperature, and force in a controlled atmosphere. Okay? So we're going to have a sample. We're going to be putting a probe on it, sitting on a stage. As we heat it up, as we cool it down, as we sit over time, the sample can change dimensions. If it changes dimensions, we're going to record how much it changes, okay? Or we're going to record if it doesn't change. Now, TMA can measure coefficient of thermal expansion along with other transitions like glass transition. It can also make viscoelastic measurements, and we'll talk about that as we go through today, like modulus. Now, how to run a typical sample. We're going to start off and show you just, boom, how to go in and run a sample. Real straightforward, okay? And then we'll go through other things, some of the specifics like calibration, etc. In this section on how to run a sample, we're going to talk about preparing the instrument, preparing and loading the sample, talk about the software, using the wizard to run the experiment, and then using universal analysis, UA, to analyze the data. Now, this is the Q400. This is what it looks like when you look at it. We're going to look at the buttons on the screen here that's highlighted, how we control it. And if we zoom in on that, we can see start and stop, reject, okay, but there's also control and display menu. If we go to the control menu, then we see we have buttons for the furnace, that's up and down. We can zero the length, measure our sample length. There's calibration that we can go from there, air cool on and off, probe up and down. Okay, they're all pretty self-explanatory. If we look at the back of the instrument, one of the first things we need to do is make sure that the purge gas is hooked up. So we've got a purge gas coming in. Purge gas for the TMA is typically, could be nitrogen, could be helium. It somewhat depends on where you're running. If you're running subambient, like down to -150, And if you're going to stay below about 300, you could use helium. Helium will give you better thermal contact down at those temperatures. If you're going to be running up to higher temperatures, for sure if you're going up to 1,000, but even much above 300, then helium's not a very good choice. Nitrogen's better. You also have up a spot here for air cool. So you can hook up an air cool line here, and that's where you would have, at the end of the run, the furnace opens up, it blows air through the furnace to help cool it down. Now, sample. One of the first things we need to do is zero the length, okay? So we're going to take the probe and we're going to zero it against the stage by just hitting the zero length that's highlighted here. Now, our sample itself, now we show here, this is a rod of PMMA, polymethyl methacrylate. And we're going to take this and we're going to cut a sample of it. And it shows the saw here that we're going to use. And this saw is, it doesn't matter exactly the brand or anything like that, but this is a low-speed diamond blade saw. And you can put a coolant in here, right in this area, like water or an oil to keep the blade cool. But if you go into the low speed, it's not a real issue anyway. But what happens is that diamond blade is going to be put right there on the sample. You can mark off exactly how much you want. You can control the speed so it goes very slow. So as it goes around, it cuts the sample without putting stresses into the sample and without heating up the sample a lot. Okay. Now we're going to place the sample on the stage. Now we talked about cutting the sample. Here's putting it on the stage. I used a different sample just for color to make it easier to stand out. But here you can see that the sample's sitting on the stage. Okay. We can use probe up to lift the probe up. You can actually reach into the drawer that's open up the door on the front of the instrument to lift the probe, but generally you'd want to use probe up. And now we can hit the measure button, and it will measure the sample length. Okay. Now let's actually talk about a little bit more about the software. That's been just some basics on the instrument. Now, from the desktop, double-click on the Q-Series Explorer icon. Okay. And then you find the instrument that's attached to your system. You find the Q400 and open that up. And when we do, this is what we see. Now, initially, there's several different views that you can look at, but the one highlighted here is the experimental view, and this is the one that I find most useful. We've got our section over here in the top right-hand corner that shows our signals. We've got a section here that's the running segment. We've got a little bit of a real-time plot here. But the main section right here in this section here is our summary procedure notes page. Okay, we'll talk about each of those tabs here coming up. If we start off just looking across the top, though, up here we can see this, we can change here what shows up in this window. Okay, so we've got, right now it's saying temperature. We got icons across the top that we can control. Here's the wizard here. This starts up universal analysis here. So we've got a lot of choices there in the software. If we look at the signal display, this shows our main signals here in the top right-hand corner. Underneath that is our method segments, what the method is going to when we hit start. There's, of course, our real-time plot. And now we've got our summary procedure and notes page. You see a tab across the top up here for each one of those, summary procedure and notes. Okay? And we'd set up all of our information there. Here's a sequence that we can set up. Now, for those that have other instruments from us that may have an auto sampler, the sequence works the same way, only the TMA doesn't have an auto sampler, so it won't automatically go to the next run, but you can program the next run that you're going to do. Now, let's go into the wizard to run an experiment. So basically we're going to click on this icon here to start the experimental wizard. It asks us what type of experiment are we going to do. So what type of probe are we using? We're using the expansion probe, penetration, macro expansion, flexural, film fiber. So we can choose which one. We're going to start off using expansion. What mode are you operating in? Now, the modes besides the standard mode, all the advanced mode, creep, stress relaxation, modulated, and dynamic, that is only if you have a Q400 EM. Okay? We will talk about that as we go down later in the class here. All right, so what experiment are we going to do? Temperature ramp, force ramp, isostrain experiment. So here's just an idea of what you want to do. Now, the TMA temperature ramp is what we're going to do at this point, okay? And that's probably the most common test. Choices here, what we're going to do. A preload force, and then our applied force. Now, we show in this experiment that the preload force and the applied force are not the same. They can be, they don't have to be, okay? Now, the preload force is the force that's going to be applied to the sample when you hit the measure button. So when it measures the sample length, that's the force that's being applied. When you start the run, that's the applied force. Normally, they would be the same, but I just wanted to show you that they don't have to be, okay? And then you can have your start temperature, your final temperature, and your ramp rate. So here we're just going to start at room temperature, which is whatever the current is. Go up to 180 at 5 degrees a minute. Now, we're using 5 degrees a minute for this example, but just realize that generally I would recommend going a little slower with TMA, maybe 2 or 3 degrees a minute. I would consider 5 degrees a minute kind of a quick and dirty experiment. Okay. If we go into advanced parameters down at the bottom, has our data sampling interval, has any additional weight that we have on the tray. We're not putting any weight on the tray. This force that we're talking about over here is going to be applied electronically. So we're not going to actually put a weight on the tray during this run. The data sampling interval is set at 1 second per point. It's going to take a data point every second, which is pretty typical. We go into post-test conditions. Post-test conditions are method in conditions. We've got a return to temperature range of 40 to 50. So at the end of the run, it's going to turn on air through the furnace and cool it down to between 40 and 50. Now that's for a standard system without a mechanical cooling accessory. If you're using the mechanical cooling accessory, that mechanical cooling accessory is always cold, and the furnace has to work against it to control the temperature. So if we have this return to temperature range checked, the mechanical cooling accessory is still going to be cooling, but the furnace is going to hold the temperature between 40 and 50. If we uncheck that with the mechanical cooling accessory on, it would just drop down to minus 70, minus 80 degrees, whatever it'll go to, somewhere in that range. We've also got marked here at the end of the run, we're going to take the probe up. That is what's suggested. It's very important if you're going into a polymer or a sample that's going to melt, because as the sample melts, if you cool it down with it still the probe down, you won't be able to get it apart. But as it opens it up, it'll string out the polymer and you can cut it. Okay? So summary so far, it just kind of goes through and says, this is what you're running, this is how you're running it, is that okay? You can go back and change it, otherwise we'd say next. And now we're going to put in our sample information, our sample name, where we're going to save the sample to. Notice the sample size. The sample size is actually put in when we hit the measure button. Remember we showed you that a while ago with that little piece of green composite. But when we put that in there and hit the measure button, it's going to measure the size. Okay? We could type in the sample here, but when we hit that measure, it's going to put the size in automatically. Operator name, any extended text, and your purge gas. Now, this shows here that we've got a purge gas of 100 mils a minute. That's pretty much standard for TMA. You could go up to a little bit higher if you had an issue with oxidation, but 100 mils a minute is pretty standard. Okay, now it just shows a checklist. Is your purge gas on? If you need cooling, is it on? Okay. Have you zeroed the probe? Have you loaded the sample? Have you measured the sample length? All that kind of good stuff. All right. If you haven't done any of this, you need to make sure you take care of that before we actually start the run. So from here, we can hit a pin, which will take us back to our regular menu, or we can just hit start the run. Now, as the sample's running, we see several things. Over here on the left-hand side, here, we see our little running man. That tells us that the instrument is running. Here, it tells us what it's doing. It's heating. Okay? Here's our current temperature. This is the segment we're in. We're ramping 5 degrees a minute up to 180. Now, notice here, this is our method. Okay? Force is set at 0.02 newtons, ramp 5 degrees a minute to 180. Now, during this run, if we needed to change this, we could do a right-click here and change this final temperature by doing a right-click and go into change segment. Okay. And actually here I'm going to show you that. So do a right-click in that running segment box. We could say modify running method, and we could change that final temperature. Okay. And then send changes. So now we've changed it to 170 instead of 180. Or you could obviously go to some other temperature. If we change screens, let me actually go back up for a second here. So this is the screen we're on, and if we look up here, this is the icon for this screen. This is our main screen that I normally use. But if I wanted to, if I use this center icon here, this shows real-time plot in this big window here, but still shows my signals and my method description. Or this other window here shows real-time plot full screen. Okay? It's just a matter of what your preference is. Now, we're going to look at universal analysis here in a minute, but universal analysis can be used during a run like real-time plot would be. When the run's over, it'll say complete up here in the box, okay? And there'll be a check mark here next to the run. That's if the run was completed successfully. If for some reason the run was not completed successfully, there would be an X there. Okay? To start universal analysis, this icon here, start UA. And now we're going to go in and use in universal analysis. So we can go in and open the data file, standard little window symbol with the file folder open. And as we go through our data here and we select the file name, this preview window shows up and says, okay, this was a TMA, here's the sample, here's the size, here's the operator, etc. That's the right sample. Okay, so we open up the file, and we've got this. We've got signals and units, data limits. We've got our name and everything again. That if we realize that, oops, this actually wasn't PMMA, it was something else, we could change that name if we needed to. But we just say OK, and here's our file. Okay, so dimension change versus temperature, and as we heat it up. Okay, one of the things that we might want to do is look at a glass transition. Now, the glass transition by TMA is defined as the onset point at the change of the expansion. So if we go in here and analyze onset point, and we can use our left mouse cursor to pick 2 points, somewhere down here before the change, somewhere up here in the center of the slope after the change. And we do a right-click in free space, accept these limits, and there's our glass transition. Another thing we might want to do is to analyze the coefficient of thermal expansion, CTE, or sometimes called the linear coefficient of thermal expansion, CLTE, or coefficient of linear thermal expansion. So there's a couple choices up here. If you look at the top, alpha at X, X1 to X2, alpha fit X1 to X2. That's normally what I'd recommend. So we can look at it down here below the glass transition. You position our cursors, right-click in free space, accept limits, and there's our CTE, coefficient of thermal expansion, below the TG. We can repeat it up here above TG, and you can see it's much higher. Not quite, but upwards of close to 10 times. Actually, I guess that's closer to 8 times. But between 8 and 9 times the expansion below TG. It is normal for polymers to expand at a much higher rate when you get above the glass transition. And that's really why we can see glass transitions by TMA. If we want to look and see how is a graph going to look when we print it, we can go File, Print Preview. So this will show us what the graph looks like. And if we wanted to, we could print the graph. Now before we go on, let me just make a comment. This course is really on the TMA, and I showed you just the brief points of universal analysis. We have a Quickstart training course just on universal analysis. So, feel free to go back and take that. That would be, I think, beneficial for you if you're not really used to using universal analysis. Some of the other topics we're going to cover. Things like calibration, running experiments using templates instead of using the wizard, using custom procedures, probes. What probes do we use? How do we change probes, etc. We'll talk about purge gas considerations a little bit more. We've already talked in a brief about sample preparation. We'll touch on that again. And then we'll talk about some maintenance and then some help. And then lastly, we're going to do the Q400 EM. I saved that for last because some people don't have the EM version. And obviously, if you don't want to listen to that, you don't have to. All right, calibration. These are the different calibrations that we need to worry about. Probe calibration, force calibration, cell constant, and temperature. And there's a couple other calibrations that we'll talk about in the EM section, phase and compliance. Okay. Probe calibration. Probe calibration can be done right from here. Calibrate, probe, pretty simple. Or that icon right there will calibrate the probe. And it pulls up this window, and it just tells you what the probe type. You need to make sure that matches what's actually there. Clear the weight tray, sample stage, press calibrate. Calibration now in progress. At the end of it, the calibration is complete. Now, I was running this on a Q400 EM, and so it prompts me that it's recommended to do a new compliance calibration. We'll cover that in a later section, but you won't have that if you don't have a Q400 EM. The probe calibration, as long as you get an OK, it passed. If it doesn't pass, you'll get an error, okay? Force calibration. Same thing, calibrate force. All right, it says make sure that the weight tray is clear. This is the weight tray down here, okay? Make sure there's no weight in there, nothing in there. Press calibrate. Now it asks you to put a weight there. So we're going to put a 50-gram weight there. There's 2 weights. We're going to start off with the 50 and calibrate. Next. And then we're going to put the 100 in there, calibrate. And at the end, here shows our window here. You can see check marks here. They're all in the green. If there was a red like this here, it failed. Okay? So as long as this all says, boom, we're done. Force is calibrated. Now we calibrate that because that's the force we're putting on the sample during runs. We're not using weights typically. We're using these the electronic force. Cell constant. First off, you go into calibration mode. So we go from up here in the main summary screen. This icon here will change our mode, so we go into calibration mode. Now, the cell constant, what we're going to run, it shows a picture down here. We're going to run a piece of aluminum and look at the coefficient of thermal expansion. And we're going to look at that as it expands over time. So we're in calibration mode. We're doing a temperature ramp. It's expansion probe. We put in all of our information here. We're going to run the sample. You can see here we ran it from minus 50 to 400 degrees at 5 degrees a minute. Very important, aluminum melts at a little over 600 degrees, 650, 660 degrees. I wouldn't recommend heating the aluminum above 600 degrees, okay? You don't want to melt that slug of aluminum. When the run's finished, you click on this icon up here that's highlighted, and that's going to start the calibration analysis. So we click on that. It asks you what calibration type, cell constant or temperature. So we're doing cell constant. It's aluminum. There's our file. It opens it. Okay. Now we can do a right click to get the dialog box, go in and choose Analyze, move our cursors to where we want it to be from, click OK, and there's our calibration for our cell constant. We can accept those results. Now notice this value here is 1.02. Should be between 1 and 1.2. It's usually going to be fairly close, though, to 1. Where you'll tend to get higher values is if you were using a film fiber assessor and you used a piece of aluminum wire instead of this block. But for the block that we're using, this is pretty typical. And we can do a right click and close the analysis. Temperature calibration. Temperature calibration, once again, in calibration mode, we program our run, only now we're running a sample of indium. We can see it sitting right here on the sample page. Stage. And we want to put the indium to make it as flat as we can as it's sitting there running, okay? And we run that, and you can see in the real-time plot window what's going to happen. As the indium melts, penetrates into it. So then we're done. We're going to analyze it. It's temperature calibration. It was indium. There's the melt point. Open up our file. And the melt of the indium shows up as penetration into the sample. We need to analyze that onset of that. So we're going to do a right click in free space, go into Analyze, pick our points before the drop and during the drop there, and say OK. And there's our onset. And there we accept the results. Okay? And we can close that window. Now if we go back to our main window here and we go into Calibrate Cell Temperature Table. Here it shows us this is our cell constant. This is our indium calibration point. Okay? That's how we can check that. Now, on this instrument, we have got this calibration mode, so you don't have to go in and zero these values out before you calibrate it. That's why there's a calibration mode. All right, let's look at running experiments using templates. Now, first off, you have to choose the mode. We're going to stick with standard mode for now. And then you have different templates. In standard mode, the templates are temperature ramp, force ramp, and isostrain. So if we're going to do a temperature ramp for now, and then you have to select your probe type, which we did earlier, but we're going to do an expansion probe. You complete your sample information. See, this is all in the summary tab. And now we're going to switch to the procedure tab. Put on our preload force, put on our applied force, our temperature range. We have advanced and post-test just like before. Remember those that we saw earlier. Then we have a notes page where we can put operator name, extended text, and our mass flow controller settings, okay? Now let's look at using custom procedures. Custom procedures, it's all the same, except instead of one of these templates here, we pick custom. We set up our information. When we go to the procedure page, we click on the editor. And so when we click on the editor here, it starts up this editor window, and now we can create basically just about any kind of method we want to. And to do that, if we want to ramp, we could go over here and double-click on the ramp, or we could grab the ramp, drag and drop it into where we want it to be. So now we're going to equilibrate, and then we're going to ramp at 5 degrees a minute to 150 is the way this is being set up here. When it's all done, we can save a procedure. The Save button here. Now, the procedure saves not only the method, but also the mode that it was ran in, the advanced and post-test procedures. So it saves more than just the method itself. So we can save that procedure. And here shows this is all the stuff that's saved in the procedure. Okay? And we can open a save procedure from right here and pick one. So if you have a couple different procedures for different types of materials, when you open it up, it sets everything just like you need it, okay? Let's talk a little bit about probes. These are the different probes on the TMA. We have a hemispherical probe, macro expansion probe, penetration probe, standard expansion probe, okay? There's some other probes we'll look at in a second, but these are all the overhead type probes. Then there's also the specifics like flexural, film fiber tension, dilatometer, and then parallel plate rheometer probes. The probe block. If we open up the door on the front of the instrument, this is the probe block here, okay? So if we want to put a probe in, what we have to do is unscrew that, so it's going to screw it counterclockwise, and then we put the probe in from the top. Once it seats down, and you'll feel it go in there, then you tighten the probe back. For the film fiber probe, this is what this looks like. The new film fiber probe for the Q400 has got this flange in it, and that flange is to really keep it from rocking, and that goes in and lines up into a cut into the stage. Now for the film fiber probe, a couple of specifics. In standard mode, the thickness should be maximum of 0.3 millimeters. If you're running in dynamic mode, you still have the same physical maximum, but typically we recommend 0.1 millimeter or less, or excuse me, 0.1 millimeter or so approximately 0.1 millimeter. The width, standard mode, has to fit in the clamp, so less than 4.5 millimeter. For dynamic mode, we recommend length to width of 16 to 1, okay? So 16 to 1 length to length to width. The narrower is better. So typically we try to run a width of about 1 millimeter, and then we'll have a length of about 16. The flexural probe, there's a new low friction aluminum fixture for the flexural probe. So this is an aluminum 3-point bend platform with 2 rollers here. They're spaced this much apart, so that's going to be your sample length. It's not recommended that this is used for thermal expansion. In thermal expansion, we want to use the quartz probe, and we'll show a picture of that in a second. But this is used like for calibration for the compliance, and we will show that later in the EM section. Purge gas. Okay, why do we use a purge gas? It's to keep an inert area around the sample and help prevent condensation of water vapor. Nitrogen is most common, but helium can give better results when going subambient. Typical flow rate's about 100 cc's a minute. I mentioned it earlier, but I do caution you, if you're using helium, you'll max out the temperature range at about 350 degrees C because it just maxes out the furnace and it just can't heat up any further. If we go to our notes page, this is where we control the flow rate, okay? And you have whatever gas is plumbed into the back of the instrument should show up there. To actually set up what that purge gas is, if we go to Tools and Instrument Preferences, in our Instrument Preferences, there's a window for the MFC, Mass Flow Controller Purge, and right now we've got it set up at nitrogen, but we could use that drop-down if we wanted to change it to helium. Now let's talk about sample preparation a little bit more. We talked about it just real briefly earlier, and I showed a picture, but if you want to get good results on the TMA, sample preparation and sample dimensions are critical. If we're running penetration or we're just trying to find glass transition, samples should be flat and parallel, or at least parallel as best you can. If you're running coefficient of thermal expansion, they have to be flat and parallel if you expect to get any data that's worth anything, okay? Prepare solid samples with low-speed, low-stress methods, like the saw we show here. So it's a low-speed saw, doesn't put much stress into the sample, and it doesn't put a lot of heat into the sample. If we're running films in tension or even softer samples, the sample should have parallel sides. Use parallel cutters. Now this shows an example of one that we sell for our DMA. Now this is actually the bigger sample that you wouldn't want to really use this probably. This is a little bit too wide, but there is one that's smaller that you could use. Thickness should be typically less than 0.5. Actually, I think we said 0.3 on the other page, so that's something that looks like I need to probably correct here, the 0.3. We'll talk about the specifics for the EM later. Now, let's look at some help information. What do we mean by this? Well, we're going to look at instrument error log, the instrument error messages, the instrument log, online help, and getting started guide, okay? Error messages. For instance, this one, probe not zero, cannot measure or move probe, okay? So that's an error that we might get. And if we say, okay, it clears it and we could change it. But what if we don't really know what that means, all right? If we go into the instrument log, and the instrument log can be accessed from this icon here, and we click on that instrument log, there's that probe that we just saw. So we can highlight that and then click on error help, and it pulls up the help for that specific message, okay? So here it tells the problem, and then it tells a solution. So this is what you have to do, all right? Press 0 length on the instrument keypad, all right? Now, it depends on the error message. Sometimes there'll be one solution. Sometimes there'll be multiple solutions. Sometimes what you'll find is that you will have 3 or 4 solutions, and the very last one will say call TA Instruments for service. So if all else fails, that's what you could do. All right, online help. When we say online help, we don't mean on the internet. We mean on your computer. It's already installed. When you install the software, it's there. All right, so if we're looking at this procedure page, and maybe there's something that we don't understand or something we're not clear about, we could click help. And the help will talk to us about that specific page that we're on. For instance, it talks about the preload and the applied force. What is that? It even gives you a good default value here, 0.02 newton, or actually 0.2 newtons, sorry, for measuring the sample length. Okay. The Getting Started guide is basically like a manual that's on your computer. So if you go to Help and Getting Started, here's our Getting Started guide. You can scroll through and go by page to page or go to specific sections. Here's Chapter 3, Use and Maintenance. If we go in there, there's one here, Cleaning the Probe Assembly. So if we highlight that, here's Cleaning the Probe Assembly. Check the probe assembly. If the probe is dirty, remove it and clean it. You can use contact cleaner or acetone applied with a soft brush or cloth. The quartz probe itself, so this was actually on the LBDT core. The quartz probe itself can be cleaned with a Bunsen burner until the residue evaporates and the probe is clean. If you do this, be careful. It gets hot, and if you touch it, you will burn yourself, guaranteed. Okay. The next little bit, we're going to talk about the Q400 EM and the specifics to that. These specifics are calibration, oscillatory compliance and phase calibration, modes of operation, and then some special conditions. After we calibrate a probe, we get this error message that we saw earlier. So if we say OK to that, and we go in and we start up this compliance calibration, it's going to step us through what we have to do here, okay? And so we say calibrate, and that's basically it. All right, we just follow the window here. The phase calibration, this is where we go into calibrate phase. This is where we use that flexural probe. We clear the weight tray and sample stage, install the flexural probe, press calibrate to begin, zero the probe, put our sample on. Here's the sample dimensions, okay? The length is fixed, but the wire that you get is just diameter. Close the furnace, press calibrate. That takes about 24 minutes. When it's all done, You'll get this window. You can say finished. Unless you get an error message, it passed. Okay. Now, mode of operation. The advanced modes that are available on the Q400 EM, not if you have a standard Q400. There's advanced mode, creep, stress relaxation mode. There's modulated TMA. This is where we're going to modulate the temperature. And then dynamic TMA. And dynamic TMA is also called modulated force. Okay? Basically, we're doing like a DMA experience, dynamic mechanical analyzer experiment. If we go into advanced, we've got custom mode, temperature ramp, force ramp, stress ramp, strain ramp, and isostrain. So those are the different tests that we can run in just the advanced mode. Creep mode, you've always got custom, but then basically you'd have a creep test. And a creep test is where we're going to put a force onto the sample for a period of time, and we're going to displace, and then we're going to take the force off and let it recover. Okay? You could do this with a film. You could stretch a film with a certain amount of force, take the force off, and watch it recover. Stress relaxation mode. Now we're going to displace it a certain amount, hold it for a period of time, and then take the force or the displacement off. Modulated temperature ramp. Modulated is where we're going to, instead of putting a linear heating rate, we're going to put a sinusoidal oscillation on that heating ramp. And the reason for using modulated is to separate out expansion from things like yielding and things like shrinkage and multiple other interference that's going on. Okay? Here's real typical conditions. We almost always use this set of conditions. Modulate plus or minus 5 degrees every 300 seconds. Slow ramp rate, 1 or 2 degrees a minute, and then over your temperature range that you're interested in. Dynamic TMA. Dynamic TMA is where we're going to modulate the force. So here we have modulate force and then a ramp rate. So once again, these are pretty typical conditions. Plus or minus 0.1 newtons at half a hertz. Okay, pretty typical conditions. Now let's look at some of the special conditions for modulated, and we've already basically talked about it. These are our recommended. 5 degrees for the amplitude, 300-second period, 1 to 2 degrees a minute for the heating ramp. You want a slow heating ramp, okay? Now the periods are very long because we have a much bigger sample, a much bigger furnace, and less active cooling than what we have on the DSC, for those that have modulated DSC. Now to use modulated TMA, you have to have the MCA, the mechanical cooling accessory, unless you're running up at a high enough temperature, like maybe 100, 150, where you get enough ambient cooling to be able to do that. Here's just setting up a modulated run here. Okay. Let's look at dynamic TMA. Dynamic TMA, force amplitude, 0.1 newton. Force frequency, 0.5 hertz. Heating rate, 2 to 3 degrees a minute. Once again, fairly slow. These are very, very typical conditions. Okay? And here we set up our information. Okay. Basically, that's it. I appreciate your time. I hope this course was beneficial for you. If you have any questions, you can send us an email. You can go on our website and send us an email. You can send us an email to thermalsupport@tainstruments.com, and that will also give you a way to send us an email if you have any questions. But some of the other courses that we have, there's Quickstart courses, advanced courses that you can take online. We have our theory and applications training courses for different instruments. Now, the actual TMA theory and application course is an online course, and it's scheduled once a quarter or so. You can have people come to your site to give you training. For instance, myself or one of my colleagues could come in and do training. There's a charge for that, but we can come in and train you and run basically your samples on your instrument and customize it like anything you want. We're always coming up with new training courses, continually updating our training. So keep checking out our website for more information. If you need further help, you can call the applications hotline, 302-427-4070, Monday through Friday, 8 to 4:30, and that's Eastern Time in the U.S. So if you're located somewhere else in the U.S. or somewhere else in another country, you have to think about the conversion there. But if you call and get voicemail, you can leave a message and someone will call you back. A lot of times what works better, especially if you're in a different time zone, is our website, our email address. So thermalsupport@tainstruments.com. This would be for our thermal equipment. The TMA would be in there, but the DSC and the TTA also. If you have a DMA or a rheometer, then you could go into rheology support@tainstruments.com. And this would allow you to go through and type in an email and get an answer back. So especially like if you're in another country, you could send that in, and even though there's a time frame, hopefully by the next day when you come in, you should have an answer. If it's a service-related problem, you can contact your local service representative, or you can contact our service hotline in Newcastle, Delaware. And so that's 302-427-4050, where someone in our service shop would answer that. Once again, it's 8 to 4:30 Eastern Time, U.S. Well, thank you for paying attention to this course. Here I realize that there's something that says our online questionnaire. The online questionnaire was actually when we were giving this course live, so it's not here for this recorded course. But please visit our website. Please send us an email if you have any other questions. And please let us know of anything that we can do for you. Okay? Thank you very much. I hope this was beneficial, and I hope you take other courses in the future.